Good morning, everyone.
Thanks, sir.
Good morning, respected DG sir and all senior officers of CPWD. On behalf of CPWD CSQ task unit, I welcome all the engineers and architects of CPWD and members of presentation team. Today's workshop is on technology neutral EPC tenders in CPWD. I kindly request DG sir to give inaugural address.
Our Honorable Prime Minister has emphasized the need to accelerate the adoption of new construction technologies to improve the pace and quality of construction. Am I audible? Yeah.
Yes.
I will just start again. So our Honorable Prime Minister has emphasized the need to accelerate the adoption of new construction technologies to improve the pace and quality of construction for addressing challenges of rapid urban growth and attendant requirements. With massive construction requirement, there is an opportunity for adopting new alternative technologies from both within the country and across the globe. This may stimulate a major transition in terms of cutting-edge building materials, technologies, and processes. Globally, there has been technological advancement in the area of building materials and fast-track prefabricated pre-engineered construction practices. CPWD envisages a lead role for itself in the execution, maintenance, and standardization of built environment. It is our vision to create and maintain a sustainable and inclusive built environment with the available resources while ensuring world-class quality. CPWD, under the aegis of MoHUA, has stepped forward to adopt new and emerging technologies in 2016. And while initially only 3 technologies were approved for adoption, the list has since been increasing. The initiative of MoHUA in terms of Global Housing Technology Challenge gave a big boost to the process of adoption of new technologies. Going forward, and to give impetus to the adoption of new technologies, it has been decided to mandate technology neutral tenders for projects. For purpose of adoption of technology neutral tenders, 4 draft circulars have been shared with all the stakeholders, about which we are going to discuss now. This workshop has been organized to have fruitful deliberations on framework and methodology to mandate technology agnostic tendering in CPWD. I welcome Professor CVR Murthy of IIT Chennai, Professor SD Bharti of MNIT Jaipur, officers of MoHUA, CPWD, and VMTPC, all the technology providers and delegates. I would now leave the floor open for a healthy discussion among all the stakeholders. Thank you.
Thank you, sir. Now I kindly request Sri Divakar sir, SETAS, to start the presentation.
Good morning, DG sir, SDG sir, ADGs, and friends. Today's workshop is on technology neutral EPC tenders in CPWD. Through this brief presentation, I will lay out the context for this workshop. The objective of the workshop is to deliberate on framework and methodology to mandate technology agnostic tendering in CPWD. Through consultation on CPWD proposal among stakeholders. The CPWD methodology for technology neutrality has been divided into 3 parts through manual and SOP circulars, through technology circulars, and contract circulars. Manual and SOP circulars, EPC modes have been linked with technology neutrality and amendment is proposed in the SOP to improve eligibility criteria and to express choice of technology for EPC modes 1 and 2. The circular technologies have been categorized, and in one circular, amendments are proposed for expression of choice of technology by bidder. Next. Draft circulars have been circulated to the stakeholders through mail and website for deliberation and suggestions. Earlier, there was no linking between EPC modes and technology neutrality, which is now proposed. Next. Technologies have been categorized. Next. Amendments are proposed in the GCC and also in Schedule F of GCC. Next. Now I request Professor CVR Murthy of IIT Madras to kindly enlighten us. Over to Professor CVR Murthy.
Namaskar. Good morning to DG Saab and all the senior officers of CPWD, as well as the younger engineers and the invitees to this workshop. Uh, my responsibility is to present the current status, the understanding of the subject of technology neutral tenders, as well as provide clarity on what are the bare essentials required for us to be able to go forward with technology neutral tenders. I have a presentation which I will start now. Can you see the screen?
Yes, we are able to see. We are able to see.
Thank you. The subject on which I will dwell today is the seismic performance assessment of new technologies through full-scale testing. The presentation will be in three parts: earthquake performance assessment, new technologies, and the road ahead. Before I do those three elements, I want to present the context of where we are in the current built environment as far as earthquake shaking is concerned. And if you flash back on time and then look at the losses that we have had, uh, it clearly shows that we have been developing the built environment without a backbone of safety embedded in that. And the rapid pace at which the construction is going on in the conventional strategy tells us that we have made a number of mistakes which we have to urgently correct. If not, we will be again back in the same mode when the next earthquake happens. You might wonder why I have been given this task of earthquake performance. The key point is that 80% of India's population is living in seismic zones 3, 4, and 5. And this picture in front of us is a seismic zone 3 picture. It is not a seismic zone 5 picture. It is in Ahmedabad city, 225 kilometers away from the earthquake. We also have had a good taste of the embarrassment of loss of 3,500 school rooms built in precast construction in Gujarat. Out of the 6,000 that were built, 3,500 came down during the earthquake. We're very fortunate that children were not inside, right? In the same campus, you will see on the left-hand side the new technology, on the right-hand side the traditional technology. And the contrast is stark, and the answers are obvious to us that we are in a great hurry to do something, but we are not doing the full, detailed, rigorous work before we accept new technologies. And I don't have to say more about the fact that there is no formal education of earthquake safety in the country in any college, and hence all of us are self-taught. As a consequence, the level of understanding of earthquake safety varies across the country, across the cadres. The summary is we have 10,000 municipal development authorities, municipal corporation, municipalities, and Panchayati Raj institutions in the country, and none of them examine safety. In this backdrop, of those collapses and this fact that there's nobody examining safety, the question is, how do we admit new technologies? And that is the question that I'll use now as the basis for the rest of our discussion. First of all, let me clarify what is earthquake performance assessment, and then I will go forward in trying to argue in favor of the actions that we are proposing. First off, there are 7 virtues of earthquake resistant constructions, and the 7 virtues are configuration, at least a minimum lateral stiffness, sufficient lateral strength, good ductility, required deformability, desirable collapse mechanism, and the amount of energy absorbed by the structure. If this is the classical understanding of the 7 virtues of earthquake resistant structures, the question is that what are we doing? What are we going to see as a consequence if we miss out on any of them? If you miss out on the first, poor configuration, you'll get undesirable twisting and actions in the structure, which will lead to immediate collapse. If you miss out on stiffness, you will lose non-structural elements. If you lose out on strength, there'll be damage to structural elements. If you lose out on ductility, individual members will rupture. If you are overlooking deformability, the collapse of the structure will happen. And if your collapse mechanism is not right, you will see that the type of collapse will become unacceptable and the level of deformation is not going to be sufficient for us. And finally, the energy, if you miss out on the energy, post-earthquake shaking duration will be very, very small. Just to give you some images, here is an open ground story structure and a L-shaped building, which is going to perform very poorly, and it did on the campus of the IOCL in the Gandhidham area. Poor configuration led to undesirable behavior, loss of lot of life on this IOCL campus. The second one is the issue of damage to non-structural elements. 70% of our costs, 70 to 90% of our costs are today on non-structural elements. And if we do not address the stiffness matter correctly, we will lose the non-structural elements immediately in small earthquakes as well as big earthquakes. The third one is stiffness. If you do not have sufficient structural elements that are having adequate stiffness, the building will see a major collapse, especially when it has unusual behavior, unusual characteristics like the open ground story. The fourth one is rupture of structural elements, which will delimit the ductility of the structure. And so we need to be watchful of that. The fifth is deformability, and a shortage of deformability in the structure will lead to collapse of the structure. And sixth is the collapse mechanism will be not the one that we are looking for when we don't take care of the load paths and the detailing of the structure, design and detailing of the structure. And finally, the earthquake energy which is fed in has to be absorbed by the structure, otherwise the structure will continue to shake. And this is what I'm looking at. If all of these are the focus items for us, I will use only one item in today's discussion, which is collapse of the structure, as a basis to argue in favor of the proposal of full-scale testing. We are clear that in the current context, we know our materials, we know how to design sections, and when we make members out of them and then go ahead, detail and construct it. But we don't know what the behavior of the structure is going to be. So we're doing the forward loop, but we're not doing the backward loop. And this is where our main responsibility lies. Unless we are confident that the new technologies in the backward loop are giving acceptable behavior, we cannot admit new technologies just on the face value of the analytical work or design calculations. And I'll tell you why we don't trust analytical work and design calculations alone without testing. Now, those of us who are into design will look at it that we have an elastic behavior. We divide by response reduction factor. We get the design strength. We design for that. We also have a serviceability level, and we look at the serviceability level deformations and we check the deformations accordingly. But when the earthquake comes, the force levels are not at this low level, but they are at minor, moderate, severe, and extreme levels of shaking. As we started this morning, earthquake is shaking under the base of the structure and not a force applied on the structure. Force is induced by the mass owing to inertia effects. And so design levels are much smaller than the actual performance levels of shaking. This is the point I wanted to clarify, that do not say that we have designed for the force and so the structure is safe. It can't be, because earthquake is displacement and displacement is much higher on the horizontal axis and the vertical axis is not in focus necessarily during earthquake shaking. Just to tell you, if you look at the earthquake resistant design philosophy, it says there's a minor earthquake, we should have no damage. There's a moderate earthquake, some structural damage can happen, and in severe earthquake, no collapse should happen. The question is, we have another fourth level beyond the severe at which the structure will collapse. And we need to quantify how much is this margin between the severe and the extreme so that we are comfortable that the structure will be approved by us for construction, especially when you're looking at mass housing. In all of this, once again, you will notice that the minor shaking is much above the deformations that will happen under strength design or serviceability design calculations. And moderate is much more severe and extreme are farther away. So there's one structure and it has to be checked for 4 shaking levels and 4 performance expectations are there. What are those 4 performance expectations? On the minor, we are saying we should have sufficient stiffness. On the moderate, we should have saying adequate strength. On the severe, we are saying we should have good ductility. And on the extreme, we are saying we should have sufficient deformability. This is where we will need to examine all our technologies on the horizontal axis, whether they can go forward or not. Now, many of us come up with nonlinear analyses. We have analytical tools now, do a pushover analysis, and then say that the structure has so much deformability and so on. You would agree that nonlinear analysis, depending on the assumptions made in the modeling and the inputs given as far as the member capacities are concerned, will decide what will be the overall capacity. Also, the current nonlinear analytical tools are only for monolithic in situ constructions and not for some of the newer technologies like precast constructions and pre-engineered constructions that we have. So we are looking for, in the structural behavior, various nonlinear states like the yielding, spalling, and then crushing of the concrete. Now you might wonder, why am I talking about all this? If you're looking at a critical building, you will want it to behave elastically during an earthquake. If you are looking at an important building like a hospital, you might at best allow some nominal structural damage in that, but not that which will cause the function to be disrupted in the aftermath of an earthquake. But in all cases, we are looking at no collapse for the normal buildings are concerned. So if you're looking at high-end constructions for special structures, you're looking at elastic behavior. If you're looking at hospital-like lifeline structures, you're looking at nominal structural damage. And if you're looking at common man houses, you're saying no collapse at all. This is what we have to guarantee when we approve a new technology. Now you might say, what is it that you are talking about, this whole levels of shaking and so on? Let me clarify that earthquake movement is actually going to be a deformation at the base of the earth or the base of the building, and that will lead to wave actions at the base. Now, depending on the natural period of the structure, the bottom is going to be subjected to a relative displacement with respect to the top of the structure by this amount of SD. That displacement is what you have to guarantee in the structure. If I have a blue level earthquake shaking, you see that the red structure D has collapsed, C is almost breathing hard, B has got nominal structural damage, and A is remaining elastic. But at the same time, if the shaking is very high, seismic zone 5, then you're looking at none of these structures surviving in that particular level of shaking. All it means is the normal understanding that strength implies safety is not true in the case of earthquakes. In the earthquakes, you have to talk about deformability of the structure, the horizontal axis capacity. For example, these green dots are the horizontal deformation capacities of each of these buildings A, B, C, D. If the earthquake is asking more than the green dot for that building will collapse. And so on, depending on the level of the earthquake shaking, you will see that the white dots are the linear range quantities and the black dots are the maximum load capacity limits here. So let us be clear that strength does not imply safety in the case of earthquake resistance, right? Based on the past earthquakes, we have noted that a number of technologies have shown very poor performance during those various events worldwide, not just in India. Unreinforced masonry, of course, all of us agree on that. Open ground story buildings, our eyes were opened in 1997 Jabalpur earthquake. We did not draw attention, but 2001 clarified it adequately. Flat slab buildings, a number of buildings worldwide are having great distress. We will soon see a large number of collapses if we continue to use this flat slab the way we are doing it right now with pre-stressed slabs. Precast buildings and structures and pre-engineered buildings. The last three are not having Indian standards for it. And I would like to underline the importance of need for Indian standards. If you understand the procedure of development of standards, there is a whole sequence of a concept to analytical work, to experimental work, and then detailed system level tests before technologies are admitted. If we haven't followed that path, then we will say that we are not ready to admit a technology. So the urgent step that we have to take is to prohibit the use of untested technologies, especially precast, pre-engineered and pre-stressed flat slab buildings. Now you might say this is not acceptable to us. I agree with you. My task is to tell you the truth and also tell you the way out of this truth. And so what we are talking about is we need to test these technologies before we go forward. Now on the picture that you see here, you see a 3-story building which is subjected to lateral actions at the top level. And this is the testing that we are looking for in buildings, as well as you can do that for bridges and other structures also. Now, you might say, why is it that you're talking about a 3-story structure for any technology to be tested? It's very simple. The bottom story is held at the base, and so this is not the normal structure that we're talking about. The top story, we have to apply a load, and so we are doing some fixtures and all that. So that is also not in the normal condition. When an earthquake happens, it will happen by itself, and so nobody is pushing at the top. So these localized forces will cause some amount of disruption of load paths and so on. The only story that is untouched by either the bottom support or the top loading point is the middle story. And this is the reason internationally also 3-story structures are tested to examine the adequacy of the design and thereby convert or clarify that this design can be taken forward into a technology. So full-scale testing becomes essential for us. The reason is in scale model testing, because earthquake shaking leads to nonlinear actions. In scale model, when you bring down the size of a column from 400 mm to 100 mm, the bar diameters have to be scaled down. That is possibly possible if you can negotiate with a steel company to give you